So we are going to get started. We are starting Unit 5 today, okay? Unit 5 is probably our shortest unit all year. In fact, if we had 2 extra days, we would test before winter break, okay? So just an FYI, in terms of the pacing, I'm really trying to stay with the College Board's recommended pacing so that we can get done in the time we need to get done so that we can study and all of those sorts of things as well. But I just wanted to give you a heads up. The calendar is up on Canvas. I just snipped this right from there. So today we're going to start harmonic motion. We'll talk about it Tuesday and Wednesday. So this is going to be like just a bunch of, this is the content. Thursday and Friday, we're going to be doing a lab related to it. So if you know that you will not be here at some point during this week, please make sure that you reach out earlier rather than later so that we can get you caught up and ready to go. So as I said, if we had 1 or 2 more days before winter break, probably this test would just happen before, but I didn't want to welcome you back on the Monday after winter break and say, hi, here's a test. That seems a little bit unkind. So we'll do a little problem solving, we'll do a little review, and then we'll test the Wednesday after break, okay? So it's just the way that things shake out. It's better to do this than not. So just an FYI as to where we are. Does that make sense to everybody? Okay. But yes, we are going to be doing things. And I put the lab right before break because I felt like that would be better than sitting and listening to me talk like the last 2 days before break. That was kind of my thought process. We're going to jump in and get started. I've got a warm-up problem here for you. This is a kind of nice bridge between the two. A couple people asked if I had the test graded. I don't. I will get them to you as soon as I can, certainly before the end of the week. Okay, so here's the situation. At the end of last unit, we started talking about springs, and, well, that's what we have here. So it's a mass oscillating. Do we know what the word oscillating means? What does to oscillate mean, Tony?
It's like bouncing up and down.
Indeed it is. It's bouncing up and down. So if you're not familiar with that word, that's one of the kind of key words of this unit. So oscillating means to, like, I'm going to just write that down, bounce up and down. Do things have to oscillate up and down? Can they oscillate different directions? They could go left and right. They could go sideways. But it's kind of moving back and forth, right? So this mass is oscillating or bouncing up and down on the end of a spring. 3 students are discussing the acceleration of the mass. So you've got Eileen, Bridget, and Chandra. Go ahead and take a look at those. See if you agree with any of them. I'm going to let you read and think by yourself first. I'll give you a minute, and then I'll give you some time to talk. Does that sound good? All right, so quiet moment. Vote. All right, here we go. So let's vote. So raise your hand if you think that Eileen's right. There are a few hands for Eileen. Bridget. It's okay. Be bold if you believe it. Believe in yourself. Chandra. Mixed bag. Who'd you vote for?
No.
Oh, I guess that is an option. I didn't realize it. Okay. No. I was confused. I forgot that it was there. None of them. Raise your hand. Anything. None of them is right. All right. So we have votes for every single option. Let's talk, shall we? What you got?
So I think that Bridget's reasoning for why Eileen is wrong is, it's wrong, but okay, so the acceleration is 0 not because the velocity is 0, but I forgot what these two are, the velocity, but because that's when the spring potential energy is going to be the greatest, so it's about to switch directions, so the velocity has to switch direction, and in order to switch directions, it has to cross 0 and then go in.
What's it?
The acceleration.
Okay.
And so I'm thinking like about just one instant after what Eileen said, that's when it's the greatest. Which might just be exactly when Eileen, just depending on how I interpret it. I might just be interpreting the wording wrong. But
end of its oscillations. As it's starting to come back up.
That change in, that's a good question.
if that is yes, then I think it's Eileen.
So Drew, can you say a little louder what you were discussing there?
It says acceleration of the mass will be largest when it's at the end of its oscillations turning around.
Okay.
Would that mean the instant that it's starting to come back?
I don't know. What do you guys think?
Oh, yeah, that makes sense.
So yeah, it's going to go down and up and down and up. So I drew this red line here. That would be like where the spring would be without the mass. Oh, go ahead.
Which end of the oscillation is she talking about? Is she talking about when it's like?
So right after that is when it.
It's a good question.
So when the spring is stretched, so like at the bottom of it, like
Yeah.
lowest point.
Well, I don't know. What do you guys think? Hey, you guys, let's have one conversation as opposed to 12. So my understanding is that here, maybe I'm going to move this line. So this would be like where it would be if it was just sitting at rest, right? Does that make sense? So like, because you did this part, right? Where you were measuring Hooke's, or you were doing Hooke's law. So you put it here and you left it here. So then you're going to pull it down a little bit, watch it go bouncy, 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 bouncy. So this would be at like its farthest point, and then it goes through this point, and then it's going to go back up here, up to here, right? And bouncy, bouncy, bouncy. And so Eileen is saying, I think that the acceleration of the mass will be largest when it's at the end of its oscillation turning around. So I don't think she's specifying if it's here or here. Does that matter? I don't know. Bridget says the velocity is 0 when it turns around, so the acceleration has to be 0. Is that true?
That's not true.
Is it possible for an object to have 0 velocity and an acceleration that's not 0? Can you give me a totally separate example of when that's true? Yeah.
When you threw the frog at the beginning, you're kind of zero velocity at the top.
Yeah. Yeah, does that make sense? So I feel like Bridget forgot that demo, didn't she? Yeah, like maybe she wasn't here that day. She was sick and didn't listen to the video or whatever. Yeah, I think that if the velocity is 0 at that point, the acceleration has to be 0. I don't think that's good logic, right? Is that okay? So I'm. Are you guys okay with that if we get rid of this one?
Yeah, we can.
Chandra says the acceleration is largest when the mass is halfway between the middle and the end, because that's when its speed is changing the most. Talk to me about that.
Isn't it more of the velocity that she's talking about the acceleration?
What do you mean?
Because when it starts at the bottom, it has to accelerate. Once it hits the middle, then it's going to start decelerating. So that the instant is at the middle of between its 2 points, and it has to have its highest velocity. So she says it's the highest acceleration.
Yeah, that's what she's wrong.
I just missed what happened there. Can you tell us what just happened back there? Somebody said
I
something.
just added that it's at 0 acceleration at that point.
Like at the red line?
At the middle line.
Is that where Chandra's talking about? Or halfway between the middle and the end.
Oh, that's like 3/4 way down.
That's what she said.
Yeah.
That's how I interpreted it. I don't know. What do you guys
yeah.
think? What did you say? That you took it the same place. So you think that she's saying? Sorry, I wasn't trying to put you on the spot. I just wanted to see what you were saying. So like here, that's what I was interpreting it as. That she was saying like that's where it's going to have the biggest acceleration. What do you guys think about that? So, do you think that Chandra's right? Or no? Help me out, you guys.
No,
No?
because the acceleration is starting to approach 0. Since the middle is 0, it's either.
How do you know the acceleration is 0 at the middle?
Because it's changing from a positive acceleration to a negative. Because it's speeding up and it's slowing down.
Does that make sense to you? Yeah? Is there another reason that we can... I don't disagree with you, Drew.
Because if it's starting at 0 here, it's speeding up to the middle. At the middle, it starts to slow down.
What does the middle represent? Equilibrium, right? What does it mean if you're at equilibrium? It means F net is 0. And if F net is 0, what does the acceleration have to be? 0. So I think that when it's at the red line, it's not accelerating at all, right? For that momentary moment of a moment, right? For that really little bit of time. So, okay, so are we voting? So we don't think it's Bridget. I think we're kind of convinced it's not Chandra. Is it Eileen or is Eileen wrong? I guess is the question. What do you guys think? Largest at the end of its oscillation when it's turning around.
Eileen is definitely correct because when the spring, or like the mass, is at the very bottom of the spring, and the spring is fully extended, it's pulling. The spring is pulling on the block with a lot of force. And if you have a lot of force, you have a lot of acceleration.
How do you know it's a lot of force?
Because the spring, it's a product of x squared, displacement squared. So,
You're thinking of the potential energy one. But the force, you were just talking about force, right? Or did I just dream that?
force.
What was it? What was it? Say it loud. Say it loud. Negative kx. The bigger that x is, the bigger that f is, right? And if that's the only thing acting, the bigger that a is. Does that make sense? And it doesn't matter if it is stretched or squished. In either case, the acceleration is going to be big, right? Yeah. Is that okay? Eileen is definitely right. I appreciated your confidence there. Yes, indeed, she is correct. Yeah. We're going to do some notes here real quick, and then we're going to get a sheet to work on. We need to talk about this thing called simple harmonic motion. You ready? So ready. When you approach a word or phrase and you don't know what it means, it's easy to break it. It's nice to break it down to get a sense. So let's break it down. What does simple mean? Easy, right? Easy to understand. That's great, isn't it? This is going to be easy stuff. Also means not complex, right? As opposed to simple harmonic motion, the other option is complex harmonic motion. That is absolutely a thing, and it's a thing that a lot of physicists study. It's really interesting, but it is much more difficult than simple harmonic motion. There is not a unit on complex harmonic motion in AP Physics 1. Okay, that's like a high-level undergrad or graduate school. Like there's a lot of big math in that. It's really cool, but we're not going to do it. Okay, harmonic. We kind of talked about that when we talked about oscillating. When I think of the word harmonic, when you think of the word harmonic, what do you think of?
Ringing.
Ringing? Yeah. Why do you think of ringing?
Because when you play a harmonic on the violin, it's ringing too much pressure on it.
Absolutely, yeah. So we think of ringing. We think of like playing an instrument, right? Or music. We think of maybe waves. Those all are harmonics, and we will get into how the harmonics work together and all of that kind of stuff, but not yet. We're not quite there yet, okay? But harmonics all come from oscillation, right? If you're listening to music, it's an oscillation of the air, okay? If you're watching harmonics, it can be in lots of different things, including a mass bouncing on a spring. So there's oscillation that occurs in all of those things. The last one's pretty easy. Motion. It's not at rest, right? Pretty straightforward. An object or system that's moving. The type of motion is this oscillatory motion, this oscillation. Okay? Simple harmonic motion is a very specific, please don't write on my tables, that's so annoying. Simple harmonic motion is a very specific kind of motion. And there are a lot of things that might appear to be simple harmonic motion that aren't. There are two things that have to be true in order for something to exhibit simple harmonic motion. So here are the two. I kind of mentioned them last week, and I said that College Board loves them. So I'm just going to let you know what they are officially so that you are completely aware and you're ready with it, okay? So the two things that have to be true for simple harmonic motion is that an object's motion must be the result of a force Okay. That number 1 is always, that is proportional. I would say force. Write this nicely. That is proportional to displacement from equilibrium. And number 2, okay, that is always directed toward the equilibrium. You've heard those 2 conditions before. Do you remember when you heard those 2 conditions before? You can look back in your notes if you want. Object's motion is a result of a force. The force is proportional to displacement and is always directed toward the equilibrium, or always in the opposite direction from the displacement. When did you hear this? What's that? The spring force. Yeah. Simple harmonic motion follows the rules of Hooke's law. F equals negative kx. Okay? So the first piece there, proportional to displacement, right? As x goes up, F goes up. The proportionality constant is the spring constant, okay? So that's number 1. And number 2, it's always directed toward the equilibrium. What part of this tells you that? The negative sign. Yeah, oops, I don't know if you can see that. There you go. Okay. Every single time that you're observing simple harmonic motion, it has to observe these things. So we're going to talk about a mass on a spring today, okay? And we're going to kind of work within this construct. And then later on, we're going to actually look at some other types of motion and see if they fit these qualifications, if they're actually simple harmonic motion, okay? Before we do that next thing, though, I need to define 3 words with you. I know, it's pretty exciting. Here they come. The first one. The first one is amplitude. Have you heard amplitude before? Have you heard of it?
Yeah.
TJ, can you tell me what amplitude is?
I can show you.
Okay, go for it.
I don't know what it is. It's like on a sine or cosine graph.
Yeah.
It's how high the what's it called?
Curve?
Yeah, the peaks and valleys.
Yeah, for sure. Yeah. So if I put some more technical words to that, but it's essentially the same thing, I'm going to say that the amplitude is the maximum displacement from equilibrium. Does that kind of match with what you're saying? TJ, do you feel? Yeah. Okay. Amplitude is marked with the letter A. And because amplitude is a displacement, the unit for it would be meters. Mm-hmm. Okay. Number 2, the second of our definitions is period. Not the part of, not speech, but you know what I'm saying, not that. But in terms of an oscillating object, what is period? Got this one too.
Yeah, it's how long how long it takes for the lines to make a hole, for it to go up and.
Yeah, that's exactly right. I love it. It's a measure not of distance, though. It's a measure of time. Yeah, it's the amount of time for one oscillation, for it to go up and down, right? To go from one, right? So if the wave is traveling, for it to go from the top to the top and back again, and we'll talk about what that means. Period is marked with the letter T, capital T. Okay? Which is for time. It has to be capital, not small. Small is just like time, like, time between two things. But the period, capital T, is always period. And the units that we're going to use are seconds. Awesome. Last one. The last one is the inverse of period. That would be the frequency. Nice. So if period is the amount of time for one oscillation, and frequency is the opposite of that, Sid's got it.
It's the amount of oscillations.
Yeah. Number of oscillations in a given amount of time. The amount of time that we usually use is 1 second. Okay? So we usually talk about it in terms of a number per seconds. That unit is, what is it? I didn't hear what you said. Hertz. Yeah. Yep. Hz. Okay? It's number of cycles per second. And the letter that we use for frequency is F, little f. Okay? We are moving into the realm of now we've got capitals and smalls. We got to keep track of what's what, right? Because you don't want to get confused. All right. Questions about this? You got it? Okay. So the next thing that we're going to do, I'm going to give you a sheet that I copied onto golden paper. Why? It's important. Don't lose it. This is a big one. I love this. I love the conversations that we're going to have about this. Come up and grab one so that you can be a part of it. Oh. All right. So friends, for some of you, this is going to be a nice review of things. For some of you, this is new. But regardless of where you're at, I want you to take a moment to understand the system that I've got, okay, before you start filling in things, okay? So here's what I'm asking. First of all, let's take a look at the left-hand side so that you can kind of see what's going on. So I've got this block on a spring. I turned it horizontally so we don't have to worry about gravity, okay? You can assume that it's sitting on some nice horizontal surface. I literally stole these and I flipped them, so that's why there is no horizontal surface. But if it makes you happier to draw a horizontal surface under each of them, you can, but that surface needs to be frictionless, okay? So it goes like this, okay, under each one of them. That's supposed to be flat too, that's how I roll, okay? So this block has been pulled away from the dotted line. The dotted line represents equilibrium, okay? And it's pulled a certain distance away. That's going to be the maximum distance away, which means that it is at its amplitude. Does that make sense? The maximum distance from equilibrium. And then at that point, it's let go. So at this first picture, it has been let go. And this arrow here shows the direction of motion. Okay? So then if you take a look at the next picture, I'm going to label these. We'll call this one A and this one B, just so that we're kind of speaking of them consistently in a moment. At B, it's just moving. It's moving right through its equilibrium position. At C, it's now moved all the way over to the left. At D, it's again passing through equilibrium. And at E, it is now all the way out again. Okay? And we could just keep this going on and on and on and on, right? Because we're just going back and forth and back and forth. Your task, and I'm going to give you a few minutes to work on this by yourself and then with a group, because that's how we roll, is that I would like you to tell me for each of these things, D is the displacement. V is velocity, A is acceleration. F sub S is the force of the spring. And then I wrote this a long time ago when I was using PE and KE, but this is U sub S and this is K in our vernacular, okay? I want to know if each of these things is at a maximum, a minimum, or 0, okay? None would be like that you can't answer the question. Does that make sense? So minimum, maximum, or zero. So I'm going to give you a minute or two to work by yourself, and then I will absolutely let you have a conversation, okay? Go ahead and get started. If you need help or you have questions, let me know. Otherwise, go ahead. Go through things. I have not looked at these answers to see if I agree with them or not, but we're going to kind of talk through them and see how we're doing. We're just going to go line by line and kind of check things in, and if we need to adjust, we are. So, again, I'm not telling you this is right or wrong yet, but I do want you to engage with it. Don't just assume that because you wrote it, it's right, or that somebody else wrote it, it's right or wrong. All right, so let's take a look at A. So A, the displacement is at maximum amplitude direction. So does that make sense that that one should be max? Sure. They have 0 for the velocity. What do you guys think?
Yes.
Why do you say 0?
Because it's reached all the way to the end and it's about to switch, so it's something.
Yeah, so it's not going. It's got to go from something to nothing, or something to something negative. So it's got to be acceleration. We said at a max. Why is the acceleration at a maximum? Okay, so one of the reasons that I want to actually dig into this is to figure out how things relate, right? So because it has a maximum force, it's going to have a maximum acceleration, right? So you might want to just write a note so you don't forget about that, right? That the force is equal to negative kx, and that's equal to ma. So if the force is really big, the acceleration is also going to be really big. If the force is really small, then the acceleration would be really small. Now, the force, which way is the force pulling? It's pulling this way. Are we going to call that a positive or a negative direction? Negative? So it's really, really big, but it's really, really big in the negative direction. So maybe instead of max, we should have minimum here. And it's all good, you guys. We're learning together. It doesn't matter as long as we're learning together. I'm going to put that force as a minimum force. Okay? Maximum in magnitude, but minimum because we're going to the left. If that's true, what do we know about the acceleration? It should also be at a minimum because the acceleration and the force are always going to be in the same direction. All right. We've got not gravitational, spring potential energy, and it says that it's at a maximum. Do you guys agree with that one? Yeah? Its displacement is at a maximum, so that makes sense. Sure. And kinetic energy you have at 0. Why? Velocity 0. So I'm just going to, again, remind myself a little bit. I'm going to say, oh, yeah, by the way, kinetic energy is 1/2 mv squared. And if the velocity is 0, then the kinetic energy has to be 0. And again, these are just friendly reminders. Remember, this is on a bright gold sheet of paper, so you're probably going to get it out in April and look at it again, after the snow is all cleared and the flowers are coming up and you have to study for a little more physics. So U sub s is equal to 1/2 kx squared. So if x is big, then u has got to be big as well. All right, let's take a look at B. So B, they have a displacement of 0. Do you guys agree with that? Because it's at where? It's at equilibrium. Equilibrium is our 0 point, so that makes some decent sense. The velocity, it says, is at a minimum. Is that okay? Does that make sense? Why does that make sense to y'all? Talk to me. It's going in the negative direction. So that means that it's got to be like minimum as opposed to maximum. How do you know that it's at a maximum speed in the negative direction when it's here? Yeah.
Acceleration equals 0.
So
it went from having a negative acceleration to having a positive after that point.
Okay.
The speed and then velocity.
Okay. Does that make sense to people? That kind of makes sense to me. I'm not gonna lie, I think I understand where you're coming from, and from a like having done this a bunch of times approach, I totally get that. But I'm gonna come back to this one in a minute and see if we can. I just want to make sure that we really, really internalize and agree with this. Acceleration, you have 0. Is that right? How do you know that one's right? Autumn, how do you know that has to be 0? She just knows. Just intuitive. Help me out, friends. How do we know? Yeah. Okay, so this is the thing that I want to do, and that's what I was trying to kind of drag out as well, right? So the way we know that acceleration is 0 is because we know the displacement is 0. All of this builds on itself. If the displacement is 0, then that means x is 0, right? Which means that f is 0. And if f is 0, that means a is 0. You have to be able to put those pieces together in order to be able to explain it, right? It is a puzzle. It all goes together. So that means f is 0, so we got that one. You also say that the spring potential is 0. How do you know that? X is 0. Do you see like all of this comes from right here? X is 0 means that, well, 1/2 kx squared also has to be 0. Talk to me about kinetic energy.
That shouldn't be maximum.
Why do you think so?
I think this kinetic energy is always positive.
Kinetic energy is always positive? Does that make sense? If the kinetic energy is always positive, then it seems like it's not 0, right? How do you know? How do you know it's at a maximum? Go for it.
The velocity is at a minimum, so it's going to be the negative a when it comes to positive a.
Okay.
And then when we plug that in, it's a squared, so the squaring on this negative, so we do the biggest one.
Okay. So I understand what you're saying, that is relying on the fact that we trust Ira and what he was saying before about why this is true. I want to know how you know that this is at a maximum. Yeah.
If the spring potential energy is 0, then all the energy has to be kinetic.
Does that make sense? There are some other ways to do it. There's some really nice calculus, and we'll get there in just a minute. But we know for sure here that in these two columns, we know that in these two columns, energy has to be conserved, right? There's no gravitational potential energy. There's no friction. So that means that if this is at a max, this has got to be 0. And if this is 0, this has got to be at a maximum. And that's actually the way that I would make this argument, is that we know that the kinetic energy is at a maximum, and therefore we know that the velocity, the speed is big. And oh, by the way, it's also going in the negative direction. So that's how I would convince myself that I know for sure, not just that my gut tells me, but that I know for sure from physics that this is at a minimum. All right, let's keep cruising here. So in letter C, it says that the displacement is at a minimum. Does that make sense to everybody? Because it's negative now, right? The velocity is 0. Same reasoning as we had up here, right? Same. The acceleration is at a minimum, maximum, or 0. I guess it could be any of those. Go for it.
I said maximum,
Why'd you say maximum?
because at that point, it's going from having negative velocity to positive velocity.
Okay.
So it went from, so like the velocity's always been increasing.
Okay. Yeah. You're doing calculus right now? Yeah. That's the thinking that I know that he indoctrinates you with. I want to see if we can get there as well. So can we get there from physics? I mean, like, I totally agree with you. I'm not saying you're wrong by any stretch. But if we know that the displacement is negative and is really, really negative, what do you know about this thing? It's what? Help me out, you guys. I'm here for you. I'm doing this for you. If x is really, really negative, what do you know about the force? Is it small? You got a negative, right? Opposite of negative is going to be positive. Really, really positive. Big, right? Enormous. And if this is big, then what has to happen to this? It has to be really big, right? Maximum as well. This right here tells you what's going on for almost everything in this chart. I really, really love this because I like that you can kind of get it all together. So we're on, what are we on? We're on C, is that right? Yeah. So this is at a minimum. So what do you know about the force? The force is at a maximum? And if the force is at a maximum, what do we know about the acceleration? Should be also at a maximum. Okay. Double check what you've got. Make sure that it's matching what we've got here. We've got the spring potential energy. It says minimum. Do we agree with that? Let me ask a quick question. Can spring potential energy be negative? No, because it's squared, right? You got your x squared. So it's going to be either maximum or zero. Which one is it in this case? It is maximum. Yep, it is. And if the velocity is zero, then indeed kinetic energy also has to be zero. Okay. I love this, you guys. Let's keep cruising. Here we go. Here's D. Take a look. Do you agree with it? Displacement is at zero because it's at equilibrium. Velocity is at a maximum because it's going really fast. That equilibrium position is where you're going the fastest, right? Going from speeding up to slowing down, that's where you're going the fastest. Acceleration is at zero because the force is at zero, because the displacement is at zero, right? We can reason through that every single time using this up here in the blue box. Spring potential energy is at zero, and therefore kinetic energy is at a maximum. Take a look at this last one at E. How'd we do? Displacement is at a maximum. Velocity is at zero. Acceleration and spring force are at minimum because they're going the other direction. It's all good, friends. We're just learning together, right? So this is a minimum. This one's at a minimum. Potential energy is at a max. Kinetic energy is at zero. Okay. There is so much physics on this chart here. Okay. I would like for you to take 2 moments. By that I mean 2 minutes, 120 seconds, and look at this with your table mates, and I want you to find as many patterns as you can. I want you to find as many patterns within this chart as you can find. Okay? Meaningful, interesting patterns. Yes, question?
Is B for velocity, is that B is the acceleration?
Because it's moving to the left.
And D is max because it's the acceleration.
Yeah. Not because of the acceleration, because the accelerations are zero in both B and D. But it's just because it's moving in that direction. Does that make sense? Yeah. So they have the same speed, they're just going in opposite directions. Yeah. Hold on a second. 2 seconds.
Ooh, these are opposites.
All right. So tell me what you found. Let's start over here. Lauren, what's one of the patterns you guys found?
We saw that the US and the K are always opposite.
Okay. So spring potential and kinetic. Okay, I'll fix it in just a second. You guys can write this down though. Are always. I hope so. What physics makes that true? Mm-hmm. Let's go here. What is another pattern that you guys found?
Oh, when it's at equilibrium, the acceleration, spring force, and US.
At equilibrium, would you say the spring force,
Spring force,
acceleration?
spring,
Oh,
spring potential energy, and acceleration.
awesome. Anything else also zero there?
Oh yeah, and displacement.
And displacement, right? Awesome. My back.
The displacement column is the same thing as the velocity column.
That is very true. The displacement column and the velocity column are the same, but shifted, aren't they? Down one row. Is that an okay way to say that? Awesome. Back table, what you got?
If there's a displacement, there's no velocity. But if there's no velocity, there's displacement.
Yes. Displacement and velocity. Can we say kind of our opposites? In that way? All right, we will jump in here tomorrow. Do not lose that piece of paper. It's important. I'll see you tomorrow. Have an awesome Monday, you guys. Thank you for your hard work today.